Welcome everyone to this first webinar from Tejas. It's a pleasure to see so many of you join from around the world. So today I'll be talking to you on what's on everyone's mind, which is 5G. Not all aspects of 5G, but only what affects optical transport, which is the main business of Tejas and probably of interest to many of you there. So what we will cover in this seminar will be three things. We will recap what 5G is, what are the use cases, and what's the architecture of 5G, only to the extent that it's relevant for optical transport. We'll then look at the requirements that these use cases and architecture impose for optical transport. But there is a new application here, which is front haul. So we'll review the requirements for both optical backhaul, familiar from 4G, as well as optical front haul. Finally, instead of just telling you everything that's out there, I'll try to make specific recommendations on how you should build your front haul and backhaul network for 5G. So what's new in 5G? Well, you must all have heard of these three things, that 5G is beyond broadband, it's beyond 4G. So broadband is going to be enhanced, and so you'll get enhanced mobile broadband. The fact is, it might not be all that more enhanced because we already have pretty good broadband on mobile with 4G. We'll have more spectrum in the higher bands, but on the other hand, the coverage will be for shorter distances. But overall, we should have somewhat better broadband than we have today, higher speeds, available, many more places. There are two other applications beyond broadband, which is low latency, ultra reliable low latency communications, URLLC as it's called. But this is 1 or 2 years away, probably 2 years away. This is largely meant for autonomous driving, V2X, that type of applications, maybe drones, but that's a couple of years away. Then you have what we loosely call IoT, as technically massive machine type communications. This is happening in parallel, but it may not be very massive in 2020, but this is happening as we speak. So we'll see some of this, but the last one will be URLLC, which is a couple of years away. The applications that everyone talks about, and they're all at various stages of happening. For IoT, it's really industrial IoT, which is driving. This is starting to happen. Factories are starting to automate using 5G, inside the campus. Largely, some of this can also be done with 4G or even 2G. But IoT is starting to emerge as an application. If you go to any 5G show, if you had been able to go to the Mobile World Congress last week, which you couldn't, you would have seen a lot of artificial reality, virtual reality, and other kinds of reality. So this is sort of the coolest application of 5G. It goes beyond just delivering HD video. And some of this will happen if you have the bandwidth. There are other IoT type applications like agriculture, which are also likely to be positively impacted by 5G, if 5G can get to all the farms and rural areas and so on. The applications that need URLLC are really the last two in this list, which is V2X, X because it can be vehicle to vehicle, vehicle to infrastructure, and some of this autonomous driving, semi-autonomous driving, and so on, what you really like to be able to do, sit in your car and get to work or home or wherever. We'll have to wait for some more time, but 5G will get there. And part of that is also getting your dinner delivered through drones at street level. Some of this drone you have seen, but in the news, but really for drones to take off, we'll need to have and like the metro lanes, you'll have to have air traffic control for drones in all the cities, and that will most likely be controlled by a 5G network. So those are the applications you can expect to see, not in 2020, but somewhere between now and 2025, and more or less, in that order. The IoT will come next. Enhanced mobile broadband is already there, and it'll get better in this year and next. You'll see a lot more IoT emerge in the short term. 3 to 5 years from now, you'll see more of the URLLC applications. In terms of technologies, how is 5G different from 4G? So one is the level of MIMO. So the number of radios you use is gone up from essentially 2 by 2 and 4 by 4 in 4G to much higher. So maybe 8 by 8 or 32 transmit, 32 receive, or even 64, right? So massive amount of MIMO. Means is you can get a lot more capacity out of the same amount of spectrum. You can also, of course, get immunity to fading and much better radio propagation, which sort of happens, which was the original intent of MIMO, and that will continue, but in addition, you'll get a lot more capacity in 5G. So that's almost the only innovation in 5G in terms of capacity. Otherwise, at the radio level, there is no new innovation in 5G compared to 4G. So it is still based on the technology called OFDM. So technology changed in GSM, which was TDM, CDMA in 3G, and OFDM in 4G. So that underlying technology has not changed. The radio technology has not changed in 5G, but MIMO, the degree of MIMO gets larger. You can get carrier aggregation. You can't get spectrum in one place, so you can get spectrum in multiple bands and put them all together. The other thing which will start to happen in 5G is a lot of computing at the edge. It's sometimes called mobile edge computing, but I just say edge computing to keep it general. This is simply because of applications like video surveillance, for example. It's impossible to carry back all that video to some central place to process. So it has to be processed at the edge. So many of these, IoT type applications which involve, say, video surveillance will require edge computing. So 5G will see some of this come together. So communications and computing will come together. Largely, networks, telcos would like networks to get automated through SDN, NFV. We've been hearing of this now for maybe 7-8 years or more. I think maybe 2012 onwards. SDN has not progressed in the carrier networks as well as it has in the data centers. And 5G looks to carry SDN to the radio network as well, in addition to, of course, the optical backhaul and so on. The most relevant aspect of 5G to transport is the architecture. So there are essentially two architectures for 5G. One is a distributed architecture, which is similar to what 4G is today. Another is a centralized architecture. I will review that. And that architecture creates a need for optical front haul in addition to back haul. And there is also some notion of mid haul, though I won't discuss that today. And so you don't want to have front haul, back haul, mid haul as separate discussions. We combine them all into cross haul. Also, to various degrees, operators would like to put everything in the cloud. There's also discussion of doing as much processing as possible in the cloud, including maybe doing a lot of the RAN in the cloud. And that also creates a need for a lot more optical transport. Broadly, let's see what will happen with 5G in the near term. So if you look at 4G today, so you have towers with 4G E-node Bs, and from there you have radio signals reaching homes, businesses, and so on. The backhaul is only partially fiberized in 4G. I would say most networks have about 20-25% fiberized backhaul. Very few networks approach anything like 100%. When 5G is added, 5G will, in the first phase, be added as small cells below 4G. So it will improve the coverage of 4G. It will improve the capacity of 4G. So by creating small cells which can, say, serve an office building or an airport or a metro station or something, and so that the macro can then serve the edges of the small cells or other areas which are not covered by these small cells. So you can think of a 5G small cell as a hotspot sitting under 4G, and essentially this 4G would sort of be the hub for 5G. So you will have maybe about 5G cells per 4G eNode B. So you would have 5 times the tower density compared to 4G, counting all of these 5G small cells as a tower. And you probably have about 10 times the connection density compared to 4G. Effectively, everybody will have a 5G or 4G connection. And they will also have multiple devices because of all this IoT and so on. So you'll have maybe an order of magnitude more connections. So this is sort of the picture of 5G that will happen in 2020, 2021. Small cells coming below 4G eNode Bs, and then creating effectively hotspots. Now, in terms of the transport architecture and some nomenclature, so you have the traditional 4G network with backhaul. I just split the backhaul into two: access backhaul, which is what the network that reaches the 4G tower, and then the aggregation, which is the network that sits behind it. What 5G does is to add a front haul network to it, which is also expected to be an optical fiber. And in this discussion, I will assume it's all optical fiber. So it's a front haul network. The interface is technically called F1. And this connects 5G small cells through a fiber optic network to the 4G eNode B. This is what I'll call the distributed RAN architecture. RAN is radio net access network. And largely, this is what we expect will happen in phase 1. This is how 5G networks will look. A more ambitious architecture is to introduce another layer in front of the front haul. So this is to separate the radios. The radio is RRU. This slide is the remote radio unit. Is to separate the remote radio unit from the 5G eNode B and have yet another network in front, which is again optical fiber, which is a front haul network based on an FX interface. So here, the radio units, can go deeper into the network, and they're all connected or centralized to a baseband unit, which is at one of these lamppost type pictures. I show 5G eNode Bs as lampposts because I think that's the natural place to put a 5G eNode B. It's a lamppost on the street. So this is the centralized architecture where radio units are separated from baseband units. But this is probably some time away. I expect most 5G implementations in the next couple of years to be of the distributed type, where you have these small cells, which are radio and 5G baseband unit integrated, connected by a front haul network to the 4G eNode B. What are the front haul requirements? So we'll first deal with the front haul network and then the backhaul network. So one of the things that's going to happen, which may surprise you, is that the optical network is going to have to provide time and frequency synchronization to the mobile network. Now, this was lost for a generation. In 4G, pretty much the optical transport network was relieved of having to provide synchronization. Synchronization was a big deal in optical. SONET and SDH, the starting term S was synchronization. So providing timing to the rest of the network was one of the key requirements from optical transport. And this continued when mobility came along in 2G and 3G, but disappeared in 4G simply because of the ubiquitous use of GPS. So every 4G eNode B had GPS. In 5G, that may change for 2 or 3 reasons, maybe 3 reasons. One is some of the 5G will be indoors, and it's hard to get a GPS antenna onto an indoor cell. You have to essentially put the antenna on the roof of the building. Secondly, even if it's not indoor, it may be below tree covers. I already showed you pictures with street lamps as their locations for 5G. That can be below a tree where there's no GPS coverage. Lastly, there is cost. If you have so many more base stations, you don't want to necessarily put GPS everywhere. So if you are an optical transport provider, you should get ready to provide timing to 5G base stations, G node Bs, as you used to do in the 3G era and before. Second, because of the front haul, largely because of the front haul, the requirement for a low deterministic latency delay is much more important in 5G than it was in 4G. 4G was the first network to demand low latency, but its demand was not very demanding. It was only 10 milliseconds one way that you had to provide, and that was not too hard to do. But 5G will require more stringent latencies, and we'll discuss how much shortly. Video traffic is something that we're all familiar, and most of us use the network to essentially watch video, including maybe this webinar, which may not be video, but at least it is some kind of animated presentation audio. But sync, timing, is another important flow that requires minimization of jitter. So this will also be a requirement in the front haul because it will carry timing traffic. Lastly, to minimize this jitter, you need to prioritize the traffic, especially the timing traffic. And so the need for traffic prioritization on the front haul is far more stringent than it has been on the back haul. So in terms of options for the front haul, so this really depends on how you split up the radio. So some of this jargon may not be familiar if you're not from the mobile world, but in the 4G, there was no split. Essentially, the base station did everything from the radio layer, the physical layer, the MAC layer, and above. There's some layer called the PDCP, the Packet Data Convergence Protocol layer. So when you first do front haul in phase 1 in 5G, we expect that the front haul will have this split at this F1 split will be at the PDCP layer. So effectively, it's not a lot of traffic compared to other splits that I'll show you. The other possibility is that only the radio gets remote, which is what I showed in the FX layer when the radio is separated from the baseband unit. And this means separation between the radio and the physical layer, which from an optical transport perspective is a lot of bandwidth. So if you use CPRI, which is also the protocol used in 4G, but it's only used within the radio network between the tower and the radio on top of the tower, then you have the same split, which requires a lot of bandwidth. Because the bandwidth needs of CPRI are very large, there is an effort within the radio community, within 3GPP, to split the physical layer of the radio into two, a lower layer and an upper layer, and that creates a new standard called eCPRI. But in the next 1 or 2 years, I expect a lot of the 5G to be distributed architecture, which is based on the F1 split, which is the phase 1 requirement here. So the front haul requirements, bandwidth requirements will be modest. It also helps to know what is the latency and timing requirements, other than just saying that it is stringent. So the distance from a 4G E node B to the 5G G node Bs, you can expect to be of the order of a few kilometers. In this picture, I showed 10 kilometers, but I think 10 is sort of the higher end. A 4G E node B today covers roughly about 3-kilometer radius, so it's probably going to be more like 5 kilometers. And then if you do one more level of split and make the radio units remote, that will probably be several hundred meters, a kilometer or so, certainly less than 3 kilometers. In terms of latencies, from the 4G E node B to the core, it's about 10 milliseconds, which is what it is today. From the 5G G node B to the 4G E node B, it will be less than 10 milliseconds, probably of the order of 1.5 milliseconds or a few milliseconds. And if you do end up making the remote radio heads really remote, that latency required on the FX interface will be a few hundred microseconds, so 100 to 500 microseconds. Timing is the most stringent requirement. So the timing error, that's what TE stands for, has to be 100 nanoseconds. And carrying this clock on the transport network is one of the most important new requirements of the transport network that 5G imposes compared to 4G. Of course, if we continue to use GPS at every 5G G node B, then the transport network does not have this burden. But as I said, that's getting increasingly harder to do for the mobile network for cost and indoor and tree cover reasons. Finally, in terms of bandwidth rate, we are used to bandwidth going up when you go deeper in the network. But front haul introduces a new notion, because front haul requires you to carry essentially, radio signal samples. The front haul bandwidth requirement could be 100G plus, and then it drops when you have the FX interface, and then between the 5G G node B and 4G E node B, it might drop to as little as 25 gig, 25 or 100 gig. Of course, in the rest of the backhaul, because of this 10x users and the capacity going up, your backhaul bandwidth goes up by a factor of 10. So it will be multiples of 100 gig deep in the network. So primarily, I think you can say that there are two key, other than bandwidth going up generally, there are two considerations for front haul, which are new. One is the latency requirement is much more stringent. It can go as stringent as 100 microseconds. 4G was more benign at 10 milliseconds. The notion of carrying timing traffic or synchronization traffic, you really have two choices. One is you keep all the frame sizes less than 2,000 bytes. So this affects video traffic, because video traffic is used to using jumbo frames, which are 10,000 bytes. So if you keep all the frame sizes less than 2,000 bytes, you can meet the timing requirements of synchronization traffic. And that is probably going to be the way that most operators would use, and that's what we recommend. The other option is that the large jumbo frames have to be preempted by frames carrying timing signals. And so that's another option. You change and adopt a new type of packet networking called time-sensitive networking, which allows you to do this preemption. But it may be simplest for everyone to simply limit all packet frame sizes to less than 2,000 bytes. That's the simplest way to go on day one. In terms of synchronization, having to provide timing is again the biggest need. And this timing need is more stringent than in 4G, because almost all 5G networks will be based on time division duplexing, TDD, which means you not only have to provide frequency synchronization, which everyone's used to doing, but also accurate phase synchronization. You need to have the accurate notion of time and not just frequency across the 5G network. In terms of transport technologies, what is new? There is a new version of OTN called OTN 3.0. So OTN 1.0 started with 10 gig. OTN 2.0 was 100 gig. So you got up to OTU 4. Pretty much all of you who use WDM today are using, or at 100 gig, or using OTN 2.0. OTN 3.0 extends this. The logical thing to do would have been to go to 400 gig. But there are several other considerations. One is 400 gig is not achievable uniformly. So you really like to go to 200 gig, 300 gig, and so on. So what OTN did was to introduce this notion of concatenating, if you will, multiple 100 gigs. So an OTUC interface, which can go up in multiples of 100 gig. So that is new in OTN 3.0. So you can get support for multiples of 100 gig. Second, even in OTN 2.0, you had a notion of ODU flex, which gave you bandwidth and granularity of 1.25 gigabits. That's been increased to give you a bandwidth and granularity of 5 gigabits. So in OTN 3.0. The third thing is that sometimes you need even 100 or 200 or 300 is not good enough granularity on the WDM side. You probably have just enough reach to send, let's say, 250 gig rather than 300 gig, and you don't want to downgrade to 200 gig. So OTN allows you now to flexibly use bandwidth of even something like 250 gig. Lastly, there is support for various other signal rates, for example, 25 gig, 50 gig, and so on, user signal rates which are needed, because 25 gig is becoming another useful interface especially in the context of 5G fronthaul. Finally, the FEC, which was part of the OTN frame, has been made more flexible in OTN 3.0. So you have a choice of various FECs to use depending on the reach and complexity that you want to implement. So there are a number of ways in which OTN has evolved in 3.0 to make it more suitable as a transport technology. Other technologies are not to be left behind. PON is evolving. GPON, it's familiar to us. That's the technology we use at home for broadband. So GPON is evolving to XGS-PON. So the X is for 10 gig Latin. Symmetric, so you get 10 gig up and down, which is important because if you're doing fronthaul, the signal is symmetric. And it can also scale further to 40 gig through NG-PON2, which is 4 WDM signals of 10 gig each. Now, GPON is in the fray simply because where the 5G small cell is likely to be deployed, it's close to the home, and GPON is already there. So GPON is a natural candidate in terms of reach to be able to carry 5G fronthaul. Packet is always competitive. Packet technologies don't want to be left behind on considerations of latency and timing and so on. So IEEE has a new standard, time-sensitive networking, which is developed explicitly to meet the timing and synchronization needs of 5G fronthaul. It's probably the most complex to deploy, but it is certainly an option. So to summarize, for fronthaul, we have really 3 options. If GPON can meet it, which will mean that the bandwidth of 5G is something like 40 gigahertz, or 40 megahertz, which is likely to be the bandwidth a lot of operators will get in, say, bands like 3.5 gigahertz. And for modest degrees of MIMO, let's say 4x4, 8x8 MIMO, GPON bandwidths will be less than 10 gig. The fronthaul bandwidths will be less than 10 gig, and they can be well supported with XGS-PON, not GPON, but XGS-PON and NG-PON2. And this is the least cost option, and it is pretty much interoperable technology across vendors. The next choice is OTN. I think OTN is pretty much going to be the first choice when the bandwidth requirements are not met by GPON. It is scalable to very high bit rates. It has inbuilt low latency support. It scores on the timing front. It can support. It can actually be used to build a multi-operator timing, support multiple timing domains. In the backhaul context, I'll also tell you that it has support for distributing timing as well. And Packet can also meet it with, especially with the new time-sensitive networking technology. So to summarize, beyond backhaul, for fronthaul, if you can do XGS-PON and that meets the bandwidth requirements, that's the least cost option. Otherwise, I think OTN is probably going to be the more popular choice. Packet is an option, but fairly complex today with time-sensitive networking, not yet widely available to implement. Let's move to the backhaul. So in terms of backhaul, the key requirement is scalability to multiple 100 gigs. SDN, I think operators have been wanting to use SDN for a long time. The data centers have gone ahead and are now fully on SDN, but it's been slower in the carrier community front. So netconf, YANG support will be required for SDN. 5G has a notion of slicing. Essentially, you can think of enhanced mobile broadband, URL, and so on as different slices of the network. There may also be a need for inter-base station communication. I say there may also be a need because we expected the same thing to happen in 4G. There was a lot of talk, for those of you who are old enough to remember 5 years ago, that there would be an X2 interface that would cause base stations to talk to each other. But pretty much all 4G implementations ignored X2. So there's again a similar talk in 5G that there will be an XN interface and so on. It may happen, but if it does, it can be met with L3 VPN capability. Lastly, you will need support for synchronization, latency. Latency is not as stringent on the backhaul as in front haul, but the need to support clock distribution is quite important. In terms of transport technologies, I would say here, of course, GPON is not even an option because the bandwidth requirements are way too high. OTN is the technology of choice in terms of scaling to multiples of 100 gig. It is inherently a low latency technology. It can support, you can build one common transport network for multiple operators because it can support multiple timing domains. In addition, if you also need to distribute a clock, distribute timing, it has this dedicated out-of-band timing channel. There's an OSMC byte which can give you a timing channel to distribute timing signals at 100 gig OTN rates. That's like a 6 megabit channel, more than enough to distribute and maintain clock throughout the network. OpEx is becoming a consideration. OTN inherently consumes less power than packet. But packet-based backhaul is largely been deployed today, especially in the access network. That is the first backhaul network that touches the base station. And packet technologies have come a long way and has now become the choice for 4G backhaul. So they continue to evolve. You have fast protection switching. Of course, with VPNs and so on, packet is a natural choice if you need to support XN traffic. The control plane is where there needs to be much more work done. SDN has been talked about. Centralized control based on SDN is what all operators want. Today, they don't have it. They have IP-MPLS, and IP-MPLS is evolving. It's a distributed controller control plane that's evolving to segment routing. So there is this debate between centralized control or distributed based on segment routing. Centralized is ideal, but it may be that IP-MPLS evolves to segment routing, and that may also get deployed. The recommended backhaul architecture would be, so you have the front haul, which is based on GPON or OTN. OTN is the wider choice, but I want to emphasize that GPON works. The backhaul network, the access portion of the backhaul network, which is the network that touches the 4G eNode Bs, is probably going to be 100 or 200 gig packet. It's already 10 gig packet today, and the 10 gig packet will evolve to 100 gig. So most 4G eNode Bs are connected by 10 gig rings, dropping 1 gig interfaces. That will go to 100 gig rings, dropping 10 gig interfaces. And behind that, we would have an aggregation network. Being a metro network, you could run the wavelengths at 600 gig each, and or multiples of 100 gig, whatever you choose based on the reach, and that's going to be based on OTN or WDM. So let me summarize. It was going to take 40 minutes, so it's more or less there. So in terms of the architecture, you have a distributed architecture which is based on small cells. So 4G eNode Bs get denser with 5G small cells. So about 5 to 10x the number of cell sites is what you can expect, but all of the new cells are going to be small cells which are on lampposts. The centralized architecture, where you further separate the radio and the baseband unit of 5G, is probably some time away in phase 2. Even 5G small cells introduces front haul in your optical transport network. So you have a new optical transport network to deal with. And the preferred technology here is OTN, especially OTN can meet both phase 1 and phase 2 requirements. If you have, if the spectrum is limited to, let's say, 40 megahertz, and if the bandwidths essentially in the front haul network are limited to 10 gigabits, which can happen in many scenarios, then you should seriously consider XGS-PON or NG-PON2 as a much lower cost option to OTN. I think in front haul, it's going to be one of these two technologies, most likely OTN. In terms of the backhaul, the access network, today in 4G, this is based on 10 gig packet rings. Many operators use IP-MPLS, but there's also a number of them who use L2, MPLS, TP. And these networks will move from 10 gig to 100 gig, maybe even 200 gig packet rings with 10 gig interfaces towards the eNode Bs. Only L3 VPN capability is needed to address any XN kind of traffic needs. Otherwise, whether you're using L2 or L3 will largely serve the purpose. In the aggregation portion of the backhaul network, speeds will scale up, especially with so much of 5G. If 5G densification holds, which is what is expected to happen, the backhaul requirements can go to multiples of 600 gig. So OTN with DWDM is going to be the metro aggregation network for mobile backhaul. And this technology can scale. OTN has come a long way with OTN 3.0. It's very flexible, and it can also carry synchronization traffic, which will be the new requirement in 5G. So I will now stop here and take questions. That's the end of my prepared presentation. So you can type in your questions on the question answers. There should be a panel. Okay. So Anu, I have to check the question answer panel. Where is the panel?
Yes.
No, where is the panel? Huh? Okay, I stopped sharing my screen. Oh, Q&A, okay. Okay, so I'm going to take the questions right now in whatever order I see them. So the first question is, does each G-node B on the light pole cater to 3 RRUs covering 3 120-degree sectors? I think the number of sectors can be flexible. 3 sectors is what we have traditionally used in 4G, but I think 3 radios does add to cost. So this could even be a single radio. The intent is to create a hotspot, to cover a few homes. So it could vary from having, so one of the 2 extremes. One is it could be just 1 radio. It could also have, beamforming to cover individual users through targeted beams. So I think the radio aspect is to be seen, but luckily it does not really impact the front haul network. Okay. The other question I have is, if my fiberization level is less than 25% for 4G networks, can we use E-band or V-band radios and avoid 100% fiberization? Well, it's a good thought. In general, we like to see more fiberization, being an optical transport vendor. So I would like to say no, but I think it would be difficult anyway, even if not for my bias. The requirements are going beyond what radios can provide. So the 4G eNode Bs you have today will most likely have to be fiberized, almost 100%. But you could run part of the front haul network on point-to-point E-band or V-band radios, or even point-to-multipoint on on one of these B-bands or V-band, where you have large amounts of capacity. But I think you should be prepared to fiberize every 4G eNode B you have today. Below that, you could choose some form of E-band or V-band radio technology. Okay. I'm looking at the next question here. Okay. The other question I have is, what will be the WDM channel capacity for metro areas? Well, in WDM, you really want to use the highest bit rate per wavelength, simply because the cost of the optics is the biggest cost in WDM. So a 200 gig interface does not cost much more than 100 gig. A 600 gig is also pretty much the same cost as 100 or 200 gig. So you really want to use the highest capacity per wavelength, and that's what all the OTN technology is designed to do, to enable you to use that at highest rate you can. If you can use 600 gig, you should do that. If you could use 300 or even 250, technology allows you to now do that. Another question I will take is, from a timing requirement perspective, which transport option is the most reliable? I think here the answer is pretty much clear. OTN is the best technology from a timing requirement perspective. There are 2 or 3 aspects of timing. I would say 3. Let's say one is just latency. I'm interpreting timing loosely to mean everything to do with latency as well as clock distribution. From a latency perspective, OTN is the best technology. It has the least latency, especially compared to packet technologies. The second thing is, if you are supporting multiple 5G networks, if you're providing backhaul to multiple 5G or 4G operators, then each having their own clock, OTN is designed to be an asynchronous technology. Everybody can have their own clock. So from that perspective, it is better. Lastly, if you're distributing a clock, then again, OTN has inherent support in terms of especially in terms of an out-of-band timing channel, the OSMC channel, to distribute clock. So from a clock distribution perspective, as an alternative to GPS, if not as a primary clock for indoor and small cells, OTN is the best transport option. The next question is, how will 5G impact agriculture, precision agriculture? What's the use of 5G in agriculture? Okay, that's an interesting question. Agriculture is one aspect of IoT. So especially with large farms, it's getting, it's a labor intensive to manage and work large farms. With 5G and instrumenting the farms with IoT for operating the farm, observing it, seeing if something is going wrong in terms of disease or so on. So essentially doing as much of the farming as possible remotely. 5G will enable that. In particular, for at least for agriculture and rural type of applications, 5G will need to have a large cell. So that's something actually from India through TSDSI, we are driving in 5G to have a large cell in 5G. Today, even in this webinar, most of the 5G I talked about was small cells densifying 4G, which is like cell radii of a few hundred meters. But there is an effort in 3GPP led by TSDSI from India to have 5-kilometer cells in 5G. And that kind of cell radius is what you need for 5G applications in agriculture and farming. Okay, another question is, can OTN help to provide end-to-end network slicing? So I'm considering OTN in both front haul and back haul. Can OTN help to provide end-to-end network slicing? So the end-to-end is not just on the transport network. The purpose of network slicing. So how is network slicing, let's say, different from QoS? You always had QoS. We talked about QoS from the very beginning in optical networks. So the difference is the radio network was never, you had resource reservation on radio networks, but that was mainly to ensure continuity of your voice call or something like that. So it wasn't designed to give you dedicated bandwidth for any other application other than to support voice. Let's say, for example, if you do LTE call, you do get resources reserved on the LTE network. So network slicing carries this forward and allows you to reserve end-to-end resources, end-to-end meaning across the radio network and across the optical network. Really, to have end-to-end resource reservation and make network slicing work, you need to have SDN implemented end-to-end in your network across the radio and the optical network. And of course, having the same technology, OTN in front haul and back haul will help. But the more important thing is to have SDN across the radio as well as the optical transport network. What's the other question? For synchronization, what will be the protocol that OTN system should support for 5G? I think so. So synchronization. So first, most synchronization in 4G is based on GPS. So that's not relevant to OTN, but there will be there are other. In this context, I should mention that almost many countries have now their own equivalent of GPS systems. GNSS. I think India has its own, so on. But really, the requirement here is to have a primary clock somewhere in your network as the source, and then distribute timing from there. So what you need is what you used to have in SONET and SDH is a timing byte to distribute this clock. And OTN provides this in the form of the OSMC byte. And that is a channel that can be used to provide timing, to carry timing signals from your primary clock and distribute it throughout the network. Okay, why is... what's the next question I should pick? Okay. So will switching to OTN help service provisioning in 5G? And how OTN will impact edge computing for low latency solutions? So OTN, so the first question is, will switching to OTN help service provisioning in 5G? I'd say of the technologies between OTN and, let's say, time-sensitive networking in packet, I'd say the more mature technology today is OTN. So OTN is probably the easier technology to deploy, the more mature technology to deploy for both front haul and back haul. It scores on almost every front, capacity, timing, and so on. Will it impact edge computing for low latency solutions? It's inherently low latency, but edge computing is sort of a different dimension to the problem. You need edge computing simply to reduce the amount of bandwidth in the network. If you can process things at the edge, mostly things like video analytics, then that reduces the amount of traffic you have to carry back. So it's sort of not quite related to OTN. Okay. What are the key changes to transport equipment from 4G to 5G? Can it be done through software upgrade on my existing 4G network? I would say unlikely, especially because unless you happen to deploy 4G backhaul network that was good enough for 100 gig, you are immediately going to have to upgrade your network interface NNI from 10 gig to 100 gig, which you probably have to look at your optical transport vendor to see if that can be done to the existing equipment. The UNI interfaces are changing. So the 4G eNode B, which got a 1 gig interface, will now get a 10 gig interface. So if you're using it for front haul, which is anyway a new network, you'll probably need 25 gig UNI interfaces as well. So speeds are changing, so it's unlikely that you can upgrade existing equipment, but you may be able to reuse and add line cards to the existing equipment. The clock requirement is more stringent in 5G, so you need at least a class B clock in your transmission equipment. So if you don't have that, you will need new equipment. If you have it, then you're fine. You will need to implement, to support 1588, which is going to be the timing protocol along with SyncKey. You'll need to implement transparent and boundary clocking. So you will need that capability in your transport equipment. So it's probably going to require quite a bit of changes in your existing 4G optical network. Okay. In preparation for 5G backhauling, what technology innovation is being made on Tejas DWDM technology? How about your NMS in terms of performance management of the links? Okay, I'll take that as a broader question. Tejas is investing in most of the aspects of OTN and DWDM technology I mentioned. We today support up to 600 gig interfaces on our OTN equipment, especially in preparation for this 5G backhaul, the aggregation portion of the network. So we have in our portfolio come up with multiple new models of equipment for the front haul and back haul network. In particular, we today are launching in 2020 or have launched 400 gig CPE equipment, one or two RU, one based on packet and three based on OTN technologies to suit different needs, speeds, and price points. We also invested in XGS-PON. So we'll be launching XGS-PON targeting both broadband and mobile front haul applications later this year. We also evolved our packet. One of the 100 gig CPEs is a packet-based CPE. So we are supporting all three, but OTN DWDM in particular is something that we have invested more in because we believe is the right technology. What will be the impact of 5G on the EPC and its migration path from 4G to 5G? Well, the first implementation of 5G will be what is called NSA, a non-standalone, which means the 5G G node B, that's the term for the base station, parents to the 4G E node B. So the 4G core remains in the initial phase. In the subsequent phase, you really have two options. You actually have 6 or 7 options depending on the G node B pairing to E node B, the G node B talks to the core, or E node B talks to the core. But most of the options that the OEMs will provide beyond the first phase is to use a new 5G core. But there is a particular option, I think it's option 6, if I remember right, which allows you to use the 4G core even when 5G becomes a standalone base station. So if you are a mobile operator, I think you should ask your OEMs to support this option 6, which allows you to use your 4G core, especially if you just invested in the 4G core. Will SDN be integrated? There's a question about Tejas. Will SDN be integrated into the Tejas NMS? Well, Tejas is evolving itself from the traditional EMS NMS architecture to an SDN controller and orchestrator-based architecture. So our approach is the EMS gets replaced by an SDN controller in phases. We have netconf and YANG directly on the network element talking to an SDN controller. ONOS is, we believe, the right choice of technology for the SDN controller. So that's where our efforts are directed to build an SDN controller based on ONOS. And then leave the orchestrator problem to the operators. So we believe operators should deploy orchestrators where they're using OSS, BSS systems today. So SDN controllers talking to orchestrators is the new EMS, NMS replacement. As an OEM, we think we should provide the ability for SDN to talk directly to our network element. So we are moving in the direction of having full netconf and YANG support directly on the network element, but also providing SDN controllers for our own equipment, leaving the orchestration problem up to the operators. The one question on GPON, the XGS-PON and GPON2 require infrastructure upgrade in terms of cables and so on. No, XGS-PON is designed to work on whatever infrastructure today you have deployed today for GPON. In fact, XGS-PON and GPON can coexist on the same single fiber, splitter, combiner infrastructure you may have deployed today for GPON. XGS-PON works on a different wavelength, so it not only does not require a new infrastructure, it coexists on the same fibers that you deployed for GPON. Okay, one more question. Why do you need eCPRI in 5G front haul? What is ORAN and why is OTN preferred? Okay, so the technology used in 4G today is CPRI. Common public radio interface, I think, is CPRI. It is very bandwidth intensive. So for example, even for 4x4 MIMO and 20 megahertz, which is what 4G uses today, the bandwidth required between the radio unit and the baseband unit is about 10 gigabits. So it's very intensive, and you can imagine that if you go from 20 megahertz to 100 megahertz, and you scale from 4x4 MIMO to 8x8 or higher, the bandwidth goes up linearly. So CPRI does not scale. So what eCPRI does is to move some part of the physical layer processing to the radio unit, and therefore significantly reduces the bandwidth requirement in the radio unit and the baseband unit. So that is what eCPRI does, and it's going to be the preferred technology for 5G. If the 5G bandwidth is low, less than 20 megahertz, you can use CPRI, of course. What is ORAN? So eCPRI standardizes the data plane, but does not standardize the control or management plane. So if you use eCPRI, you are stuck with using the radio unit and the baseband unit from the same vendor. So ORAN standardizes this so that you can start to get radio units and baseband units from separate vendors. And that's the reason ORAN is preferred by operators. ORAN is open RAN, and that's what they're trying to do, keep the radio unit as open. Why is OTN preferred in the front haul? If you want to, so to the extent that optical transport has been used in front haul, it's been dark fiber, really. Today in 4G, the radio unit and baseband unit is dark fiber. So there is no front haul transport network, it's just a dark fiber network. But if you don't want to burn dark fiber for front haul, and it can be a lot of dark fiber, because if you have, let's say, 10 5G base stations, you'd have to have 10 pairs of fibers, or at least 10 fibers to go there. You may have that. If you want to multiplex, then OTN is the most efficient multiplexing option, given the rates that front haul will need. So, and if you're building an optical transport network serving multiple operators and multiplexing onto one common stream, then OTN is the technology of choice. I think I have 1 or 2 minutes, so maybe one last question. What will be the IP transport network? So I'll take that. I've not answered much about IP in this. Today, if you're a mobile operator doing your own backhaul, a lot of the times your backhaul is based on IP MPLS. If you're a wholesale operator providing bandwidth to mobile operators for their backhaul, then you're probably using MPLS TP, some L2 technology, or maybe even OTN, but largely it's been L2. So in terms of IP, there's a need for L3 VPN clearly for base stations to talk to each other. That's one requirement. If you move to SDN, so you need layer 3, and MPLS may get replaced by segment routing. But if you move completely to SDN, which is a centralized control plane, then you really don't need MPLS or even segment routing. But that's a choice each operator has to individually make. Okay. Okay, I'll take one more question. I'm a wholesale bandwidth provider currently offering 4G mobile backhaul services. Would my transport requirements for 5G be different from that of a mobile operator? You are serving the same E node Bs and G node Bs, so in that sense, your network requirements are, your equipment requirements are similar. But you also have probably other customers. You're serving internet access to businesses, maybe homes. If you're a wholesale bandwidth provider, you may have ISP customers also who are not mobile operators. So you probably require a transport network that can support 4G, 5G, front haul, back haul, as well as broadband needs for GPON and internet access for businesses. So maybe we'll have another webinar to address that a month or so from now. I have now reached the end. I'm 1 minute over. So I'd like to thank everyone who took the trouble to join us today. I hope you found it useful, and I welcome feedback. If you hope you could fill the feedback form. If not, feel free to send an email to marketing@tejas-networks.com telling us what you liked, what you didn't like about this webinar, good, bad, all feedback is welcome. And thank you again. I look forward to the next webinar. Thank you.